In video 4 of work, we're going to consider some more complicated problems for computing the work, such as the example I'm going to do, as well as to look at one of the advantages that you can do with using work, which is if the force does no work, you can basically neglect it from the problem. In general, the amount of work done by a force on an object can change as the object moves along a path. This could be because the path is curved and the force stays in the same direction, and so the angle between the two vectors changes. Or it could be because the force changes as you move along the path. So we're going to take a look at that. In this case, we're going to look at the work done by gravity, and we're going to do it for different parts of the path. So in this path, it's going to move around this rectangular path, and I'm going to break it into 4 parts where I look at the force of gravity on the ball over these 4 different paths. Now in this case, gravity is pointing the y direction down. Okay, so it's what we know it to be. It's mg, and we're told the mass of the object. And so here's how we go about this. We do exactly what we did the last video. We compute for each single path separately. So in this case, from path on 1, so this is from here to over there, we have the following. The work done on part 1 is equal to the force dotted into the displacement vector, delta r, along part A. Well, the force is 0 I hat minus, my fault, minus mg j hat, and then we're going to dot that into a displacement along here, and the displacement is 2 units along x, 2 meters I hat, and it's plus 0 meters j hat because I didn't go along the y. So 0 times 2, 0 newtons times 2 meters, plus a minus mg times 0 meters. And what do we get? Well, this is 0 and this is 0. Now you could have just as easily said, look, the vector is down this direction. The path is perpendicular. The angle between it is 90. So the cosine of 90 is 0. Okay, that's a perfectly good way to do this calculation too. Either way, you should find that on path 1, there is 0 joules of work done by gravity. Alright, so gravity doesn't speed up or slow the ball down on this part of the path. Let's go to the next path. In the next part of the path, we do exactly the same thing. In this case, we have 0 I hat minus mg j hat. Force doesn't change, but our dot product is now, we're not changing x, so that's 0 meters I hat, but we are changing y. Y is going from 0 to 1. So plus 1 meter j hat. 0 times 0 is 0. Then we have plus a minus mg times 1 meter. Alright, so the work in this case would be equal to minus 2 kilograms times 9.8 meters per second squared times 1 meter. You plug all that in, you get minus 19.6. Oops, my fault. I lost my 0.6. 19.6 joules. So along path 2, as it goes from here upwards, the gravity is doing negative work. It's slowing the ball down on the way up. Let's do path 3. In path 3, we had 0 I hat minus mgj hat again. force not changing throughout the problem. But this time I'm not changing y, I'm changing x. And I'm changing it from 2 to 0. So minus 2 units along x, 0 units along j. 0 times minus 2 is 0, plus a minus mg times 0 is 0. So I get no work done, because again the force is perpendicular to the displacement. And along the fourth path, in this path we have 0 I hat minus mg j hat, and then I dot that with not changing x, but y is going from 1 to 0. That's minus 1 meter j hat. So 0 times 0 is 0. Minus mg times minus 1 is a positive mg times 1 meter. So that would be 2 kilograms times 9.8 meters per second squared times 1 meter. And we do that, we get 19.6 joules. Whoops. Again, I left off my 0.6. Seem to be doing that continually. So that means when it's falling, it's speeding up. Work by the gravity is positive. If you take the whole path, actually I don't want to use the term net, use net usually when you're talking about all the forces, so let's just call it total, because we're only talking about gravity, although in our case that is all the forces. We're talking about W1 plus W2 plus W3 plus W4. And we know some things. We found that this was 0. We found this was 0. And this was minus 19.6 joules for W2 plus 19.6 joules for W4. W total is 0 joules. Object returns at the same speed. It turns out that no matter what path you take with gravity, if you end up back where you start, you will find that the total work by gravity is 0. A force where this is true is called a conservative force, and we'll study more about them later. The way to actually compute their works easier is that we can develop formulas since it's independent of the path, and the negative of the work done over that path is called the change in potential energy. Now, in some cases we found that the work done was 0. Turns out there are 4 times in which that can happen. The work done by a force is 0 if any of the following 4 cases hold. First, if you don't have a force, then that invisible and missing force can do no work. Second, you can have a force, but if the object is not displaced, then the force does no work. You can also have, like we did in the previous example, and find that the force is perpendicular to the displacement. So you have something like the force is here, but the displacement is there. In that case, the force does not cause the speed of the object to change. It simply causes it to follow a curved path. An example of that would be the centripetal force that does no work. And last, and the hardest one is that you can have a case in which when you plot this, you find that there is some area under the force displacement graph, and the amount of area plus and minus over the path happens to equal. We had that in our case. If I had drawn it for the amount of work and everything, we would have had a graph that looked like this. This would have been path 1. Then we would have had path 2. Then we would have had path 3. And then we would have had path 4. Where that's the force. And what we would have found is that this was minus 19.6 joules. And this in here was 19.6 joules. And the total amount of area on one part of the path was canceled by the amount of area on another part of the path. So the net example was 0. Very quickly, let's take an example of one of these things about perpendicular. Take the Earth pulling on the moon. So there is some force here. But I don't have to compute that. I don't have to know the mass of the Earth and the mass of the moon and the distance between this. Although there is Newton's universal law of gravity that'll let me do that, I don't need it, because although the force is not 0 and the displacement is not 0, the moon is moving around, the work is 0 because the angle is 90 degrees. So the gravitational force of the Earth on the moon neither speeds up nor slows down the Earth. But the velocity vector is changing. The moon certainly is accelerating. If I use forces, I have to account for that. But if I work from the work approach, I can just ignore the gravity altogether. Remember, the key thing is that unlike the force method, it's possible in the work approach to ignore forces if they do no work. All right, we'll see some more advanced stuff in the next video.